All right, functions. So, our first online lesson, we are going to revisit matrices. So, we're going to redefine what a matrix is. That's the goal here. We're going to we are going to look at a lot of different properties of the matrix. Before we get started, I just want to bring up the ways that we defined it before. A matrix, as first defined in class, was a box of numbers. Very, very exciting. Numbers starts with an N. And then we got a little bit more. We started to apply the matrix, and we used it to solve system of equations. So a matrix was used for a method of carrying out Gaussian elimination. But what I want to do is I want to forget about these two definitions and rigorously define what a matrix is, and then start to look at its different properties. See if we have different types of operations that we can use, and so on and so forth. So, prop 1. A matrix has a certain number of rows and columns. Called the dimension of the matrix. We often call the dimension of a matrix, we call it the size or the order, but I usually just refer to it as the dimension of the matrix. These terms are synonymous: size, order, dimension. We also, when talking about matrices, we designate them using uppercase letters as opposed to lowercase letters. The elements within the matrix, we use lowercase letters. For example, we may talk about a matrix A. This matrix A, we'll talk about the elements within the matrix using a lowercase letter as well as subscripts. I, J, double subscript. We call this double subscript notation. And it can be used to define a matrix as such. A with subscript ij is the element in the ith row and the jth column. So here is, let me go ahead and actually put some numbers inside of the matrix A. So here we go. Here's a matrix. Let's go ahead and have 3 rows and 4 columns. Right. So if I want to talk about 2, because we're using the capital letter A, we're going to use a lowercase letter A, and this is in the second row, third column. So I'm going to have the subscripts 2 and 3, and A subscript 2, 3, 2 comma 3. That is the number 2. So that's how we're going to notate things. One thing that's interesting as well is that we can use this notation format to more complex. Now we can define new matrices in a more complex way. So for example, let's talk about a matrix B, and B, its elements, that's a subscript I, subscript J, its elements are going to be such that it is the element in my A matrix, I'll go ahead and IJ, but then I'm going to add to that element the product of whatever row and column it is. That's kind of interesting. All right, so what's that going to be? Take a second to fill out matrix B as I get myself set up. And once you got it filled out, go ahead, check with me. You can go pause if you want. But let's see. So like B11 is going to be, well, it's the element in the A matrix in the first row, first column, so 2, plus the product of the first row and the first column, 1 times 1. So that's going to be 2 times 1, 2 plus 1 times 1, which is 3. So 3 is going to go there. And once again, go ahead and fill this whole thing out. Let me go ahead and do another arbitrary one. Let's go ahead and do, let's say, the 4, 3. So the fourth, oops, sorry, that doesn't exist. Let's go 3, 4. So the third row, the fourth column, right, so that's going to be 6, and we are taking the third row and the fourth column, so 3 times 4, that's 12 plus 6, that's 18. So this is an 18. I'm going to go ahead and fill this whole thing out. So we got 3, 2, 0, 8, 3, 11, 8, 7, and 8, 7, 9, 18. All right, so there's your B. Hopefully you got that right. Yeah, so we can talk about matrices using this filled out notation, literally what it is, but we can also use this more concise notation, and we can use this notation to produce new matrices in interesting ways. All right, so let's continue to look at some of the properties of matrices. Two matrices. Of size m by n, right? So two matrices size m by n are equal. Handwriting's hard to get sloppy, sorry. If and only if, one, they have the same size, m by n. Two matrices are equal if and only if they have the same size, and A sub ij is equal to B sub ig for all values of I and j. So I is going to be the row, and j is going to be the column. All right, so two matrices are equal if they contain all of the same elements in the same spots. Let's go ahead and call that property number 1. Property number 2, two matrices, we can add two matrices. Matrix addition. If A and B are of size m by n, so once again they need to be the same size, A plus B is going to be C such that Cij is equal to Aij plus Bij. All right, so you're going to take each element in each spot that correspond with each other and sum them. So A11 plus B11 would be C11. A23 plus B23 is going to be C23. So you're going to add like positions in the matrices. Notice that the size of A plus A plus the B, they must be the same size, and the resultant matrix is the same size. All right, so property 3, scalar multiplication. All right, so scalar multiplication. If I take a number and multiply a matrix by it, all that's going to do is it's going to take every element of A and multiply it by that constant. So for example, 2 times the matrix 1, 2, 3, 4, that's going to be the matrix 2, 4, 4, 6, 8. So scalar multiplication hits every element within the matrix. All right, property number 4. Matrix multi. Let's come back to that later. What I want to talk about is matrices as a group. All right, taking it way back to September. Matrices as a group. That's supposed to be a question mark. All right, let's talk about this. So what I mean more specifically is, let's pretend like I have, all right, some new notation, some bold, blackboard bold, capital letters, M. So let's take all the matrices of size mn. So like every single possible matrix you could think about of size 2, 2, or 2, 4, or whatever. Is this matrix, this set of matrices, a group? All right, so let's see. What are the properties that you need to check if something's a group? Why don't you go ahead and pause now and remember that and try this out. And then once you've thought about it for a little bit, we can talk it out. All right, let's look at closure. Like, is the set of matrices closed under? Oh, let's add a. Oh my gosh, I'm so sorry. Let's add a operation, matrix addition. So, is it closed? Is A plus B contained in the set of matrices m by n? Well, yes, we've already discussed that. When you sum 2 matrices of the same size, you get a matrix of the same size. So if I take 2 matrices of size 2, 2, and 2, 2, I'm going to get a matrix of size 2. So closure works. We are on our way. Let's look at associativity. All right, let's remind ourselves what that means. We have A plus B plus C, A plus B plus C. Does grouping matter? Are these two things equal when we're dealing with the object's matrices? So let's look at A plus B plus C and A plus B plus C. All right, so I'm just going to talk this one out in like the span of 10 seconds. We are doing addition. Addition's associative. So, I mean, just take a second to convince yourself. We're not going to do any like axiomatic proofs here. So we are associative because we're adding elements within a matrix. So we're associative. All right, cool. Let's go ahead and look at property 3. Is there a identity element? Take a second to think about that. Is there an identity element? Is there a matrix that when I add it to, let's call it capital I, that I get A? What is this matrix I? Right, obviously, yes, we have the 0 matrix, lot, just tons and tons of zeros. This is our identity for addition. Cool. Let's go ahead and think about inverses. Is there an inverse element? Okay, so inverse, question mark. All right, so we need to find a matrix such that when I add it, let's call it a inverse, I get the identity. So I need a matrix. When I add it, I get that 0 matrix. I'm just going to write it like this for lazy sake. So A plus A inverse equals the set of 0. Does this thing exist? Well, yes, because we have the multiplication of a scalar. We can do A plus -1 times A. That gives us 0. So, yes, we have an inverse element for addition. And then, last but not least, let's look and see if this thing is abelian. So do we have commutativity? Property 5. Take a second. Yeah, A plus B is equal to B plus A. Addition is commutative, so all right, so this is the set of matrices m by n, and the operation addition. This is an abelian group. Cool. Let's keep exploring the properties of matrices. Let's keep going. All right, so addition. Pretty straightforward. But what about matrix multiplication? That kind of needs some fleshing out. All right, so let's try to define what matrix multiplication is. So it could kind of be anything, to be honest. Math is defined, so we could define it like, I don't know, take each element in each set and multiply them and basically do what you do with addition. But that isn't actually how we do it, and let me try to justify the reason why we do what we do. So before we even come up with a definition for matrix multiplication, let's look at a scenario. So suppose we have a company that assembles boats. Who doesn't like a good boat? Woo. Suppose we have a company that assembles boats, plural. They don't just make one boat, they make multiple boats. Right. Furthermore, this company makes small, medium, and you guessed it, large boats. So think like kayak, canoe, yacht. This company makes small, medium, and large boats. Cool. Right, in order for this company to make a boat, they must cut wood. They must assemble the wood, and they must package and send the boat. So cut, assemble, and package. There are 3 elements to making a boat and getting it out to the consumer. finally, let's talk about how long and how much it costs to do these things. And that's kind of how we're going to frame this whole thing in terms of creating and selling and looking at profits. So let's say it takes 1 hour to cut a piece of wood. It takes 0.5, sorry, let me rewind. It takes 1 hour to cut a small boat. It takes half an hour to assemble a small boat, and it takes 0.2 hours or 1/5 of an hour to package a small boat. It's going to take 1.6 hours to cut a medium-sized boat. It's going to take 1 hour to assemble it, and then 0.2 to package, and then it's going to take 2.5 hours to cut. It's going to take 2 hours to assemble, and it's going to take 2/5 or 0.4 hours to package a large boat. So all that information I just gave you, super cumbersome. Let's turn that into a matrix. Let's try to describe all that information I gave you in matrix form. So I'm going to call this matrix L. And matrix L's dimensions are going to be, let me back up a little bit, lower myself down. Right, so the first column is going to talk about cutting. The second column is going to talk about assembling. And the third column is going to provide us information on packaging. The first row will describe a small boat. The second row will describe a medium boat. And the third row will describe a large boat. So we have 1, we have 0.5, and we have 0.2. If you rewind and listen to my word problems info slower, you'll remember that I said the small boat takes 1 hour to cut, half an hour to assemble, and 1/5 of an hour to package. Likewise, we have 1.6 to cut a medium. It took 2.5 to cut a large. It takes 1 hour to assemble a medium. It takes 2 hours to assemble a large, and it's going to take 0.2 of an hour to package a medium and 0.4 to package a large. All right, so already we are using a matrix to describe things happening in the real world. We are using this array to provide information for 2 different sets of information. All right, so let me go ahead and just grab this information here and take it to the next page. So I'm still getting used to this program. So we have our labor matrix here. This is how long it takes to do things, and this is all in hours here. I want to introduce a new element to this word problem, and that is 2 different factories. So we're going to have factory A and factory B. Now factory A and factory B have different wages for their employees. All right, so with that said, let's pretend like factory A is in San Francisco. It costs a lot of money to live in San Francisco, and factory B is going to be in, I don't know, rural Oklahoma, someplace that costs less to live than a major city. All right, so factory A, we're going to use a matrix to describe how much it pays its employees. So it pays its cutters 12, whereas factory B pays its cutters 10. It pays its assemblers. Let's go ahead and say 9. Factory B pays 8. And then the packaging 6 and 5. So we have 2 matrices here, and they represent a lot of information. Right? And you can imagine how this might get more expansive depending on how actually complex your business is. Yeah. So with all of this said, I have a few questions. Question number 1. What is the labor cost to produce a medium boat at Factory B? All right, so think about that for a second. And what does it cost to produce and sell a medium-sized boat at Factory B? So if I go back, I look at this, Factory B medium, so it takes 1.6 hours to cut a medium-sized boat, and Factory B pays $10 per hour to cut a boat. So that's going to be, let me go back here, 1.6 hours times the $10 they're getting paid. All right, cool. Once it's been cut, it then gets passed to assembly. It takes 1 hour to assemble at a rate of $8 per hour. So 1 times 8. And then, let's jump back. It takes 0.2 hours at a rate of $5 an hour to package. And that is going to be, what is that? 16 plus 8 plus, my brain shutting down. I'm going to go ahead and write this as 2/10. And then, look at that. It is all right, we got 16, we got 8, and we got 10 halves. And we got 16, we got 8, and we got 1. So that, what is that? That's $25. Cool. All right, so we use these matrices, this column, sorry, I misspoke, this row, and let me go ahead and use some more colors. That was one of the recommendations. This row and this column to determine how much money Factory B charges for a medium boat. So 1.6 times 10, 1 times 8, 0.2 times 5. All right, and that gave us $25. All right, I have another question for you. What is the labor cost for a large boat at Plant A? Large boat at Plant A. Being a little bit lazy here with my question. What is the labor cost to produce a large boat at Plant A? Let's take a second to calculate it. But if I jump back here, a large boat at Plant A, I care about this information, and I care about this information. Oops. Okay. So you get 2.5 hours at $12 an hour, 2 hours at $9 an hour, 0.4 hours at $6 an hour. That is going to be we got 2.5 times 12 plus 2 times 9 plus 0.4 times 6. And that's going to be, I'm just going to go ahead and pump this into a calculator. $50.40. All right, so once again, we did a very similar operation. Green, green, row, column, and we're getting good information. We're figuring out how much the labor costs for different scenarios is. What happens if I just do this with every single row and every single column? So if I take, let me jump back. If I take every single row and every single column, and I do this process, 1 times 12, 0.5 times 9, 0.2 times 6, and so on and so forth. Let's see what that looks like. So let me jump over here. We have 1, we have 0.5, we have 0.2, we have 1.6, we have 1, we have 0.2, and we have 2.5, we have 2, and we have 0.4, we have this. All right, let's go ahead and look at that other matrix. We have 12 and 10, 9 and 8, and 6 and 5. And if I want to know every single scenario, each one of these spots can represent one of those scenarios. So 1 times 12, 0.5 times 9, 0.2 times 6. I've already done the calculations here. All right, so I'm going to go ahead and transfer those matrices to this page. We have a small, medium, and large boat to cut, assemble, and package. It takes 1 hour, then 0.5 hours, then 0.2 hours to do those 3 things for small boat. It takes 1.6 hours, 1.2, and 2.5, 2, and 0.4. This is the matrix L. It represents the hours to do certain things based on the size of the boat and the process in production. We are going to then look at how much it costs at each place. So at factory A, it's going to be $12 an hour, $9 an hour, and $6 an hour to do those 3 operations, C, A, P. And then at company B, it's going to cost $10, $8, and $5. And let's look at how much it costs to completely produce a boat at each of these companies. So 1 hour, $12 an hour. So small boat, it takes $1 an hour to cut. It takes $12 an hour to cut for 1 hour. So that's 12. So this and this gives us part of the cost. Go ahead and use new colors. So 1 and 12, 0.5 and 9, 0.2 and 6. Those give us the cost. And that's going to be, let me break out my calculator. Give me 1 second. That's 17.7. Same thing, 1 hour at $10 an hour, 0.5 hours at $8 an hour, 0.2 at $5 an hour. That's going to be 15. And I'm going to go ahead and pause for 1 second and then just pump out these calculations. All right, I'm back. 29.4, 25. Notice it always costs more at company A. 50.4 and 46.4. All right, so the amount of hours of the wages that the people are making, that gives us, when we do this process, that gives us the cost for every scenario. Right. So what we've just done here, this is what matrix multiplication is. It is multiplying the first matrices row and the second matrices column pointwise. So 1 and 12, 0.5 and 9, 0.2 and 6. And you do that with every possible iteration. This is what matrix multiplication is. Right? We are not simply, doing 1 times 12 and 0.5 times 10 and 0.2 times, oh, there's nothing there. Right? There's a very precise way in which we do matrix multiplication. It is row times column. And that number, that single number, is what's placed in the ith row and jth column. So row 1, column 1 is going to fill row 1, column 1 in the resultant matrix. What's important to note before we proceed is another aspect of matrix multiplication is that the number of columns here must match the number of rows here, or this entire process wouldn't be possible. If there was like another column right here for, let's say, distribution, this matrix would not be able to, it wouldn't be compatible with this matrix. It wouldn't know what to do with this distribution column. So the amount of columns needs to be equivalent to the amount of rows in the second column. Another problem with this is, not problem, but thing to note is that A times B does not equal B times A. It's very necessary that when you multiply matrices, if you're given a matrix with m by n rows, m rows by n columns, and you're going to multiply it times another one, right? That new matrix, that second matrix, must have n rows, right? This number doesn't matter. This could be like m and o. Let's call it p. Let's stay away from o. M times n and n times p. This must be the dimensions of the two matrices if you're going to multiply them. Another fun thing is that when you multiply these two things and you get a matrix, the dimensions of C will be m times p. The n's kind of go away. It's going to be m times p. If I jump back to this scenario right here, right? This was 3 by 3. This was 3 by 2. And the final answer was 3 by 2, right? This is 3 by 3. This was 3 by 2. And the final answer is the 3's go away. And this is 3 by 2. These are things that you will notice as we proceed through more matrix understanding. All right, so let's get just a more simple example in. Let's move on from word problem land. So example. Here's a matrix. It's going to be 3 by 4. And I'm going to have 1, 7, negative 3, 10. 0, 6, 5, negative 2. And negative 1, 4, 8, 0. And I want to multiply this by, and we don't actually put a symbol when we do it, just like when we multiply numbers. I'm going to go ahead and multiply this by 6, negative 4, 0, 2, 3, 5, and 9, negative 1. All right, so what does this look like? Well, first of all, let's double check. This is 4 by 2. So before we even proceed, we know that the final answer is going to be 3 by 2. Cool. All right. And then we're going to multiply rows and columns. So 1 and 6, 7 and 0, negative 3 and 3, and 10 and 9. So we got 90, negative 9, 81, and 6, 81. That's 87. All right. We're going to multiply row by column. The first row and the second column will become the first row, second column spot right here. It's not 0. So we got 1 and negative 4, 7 and 2, negative 3 and 5, 10 and negative 1. We get 10 and 3. That's going to be negative 15. 0, and we're going to do the same thing. Row, column. Row 2, column 1 becomes the row 2, column 1 spot. So 0 and 6, 0, 0 and 6, 0, 5 and 3, 15, negative 9 and 2, that's going to be negative 3. And I'm going to go ahead and pause and just calculate these for us. You can go ahead and pause too if you want to do it yourself. All right, this is 39, this is 18, this is 52. So just one last time real quick. Negative 1, this third row, second column is going to become the third row, second column spot. Negative 1 and negative 4, that's 4, plus 8 is 12, plus 40 is 52, plus 0 is 52. Cool, 52, boom. All right, so let's keep going. Gotten to the point where I run out of pre-made slides, so give me 1 second to make a few more. All right. All right, we're back here. All right, so let's start looking at the properties of matrix multiplication rather than just the operation itself. All right, so let me just fix some stuff. Okay, so the first thing I want you to do is ask yourself if you think that matrix multiplication is associative. Is it associative? All right, so we're going to be a little bit more relaxed about this, but let's just kind of convince ourselves. The proof's pretty overwhelming. I don't really feel like doing it. Feel free to explore if you want, but let's look and see if this is true. And just like real quick, let's pretend like this is, so let's define it so that we can in fact do the multiplication. So this will be m times n, b will be n times, sorry, n, we want the multiplication to work, so we need these two things to be the same. This will be n times p, and then c will be p, let's call it PR. All right, so multiplication works here. Over here, we're going to have m by n, n by p, and p by r. All right, so a times b, that's going to be a matrix that is m by p. Oh, well, actually, let me rewind. Sorry. We have to do BC first, so that's the whole point of the grouping. N times P, P times R, that's going to be N times R. And then we have over here M by N, and then so that becomes that. And then these become M times R. Cool. So hopefully, right now we're only looking at, are the dimensions going to be consistent? It's a much more complex question that, not complex, let me rewind, not complex, just tedious, that this does in fact work. Just give yourself some arbitrary dimensions and just do the algebra. It's miserable. I'm not going to do it here. M times N, N times P, that's M times P. So notice it's different. This level here is different. P times R. And then this one is going to be M by R. Oh, look, they're the same. So the dimensions are at least the same. You go ahead and convince yourself that it is in fact associative. But I'm going to go ahead and tell you that it is associative. How about, is it commutative? All right, you take your second to think about it, and The answer is definitely no, and there's like a lot of ways you can think about it. One way is like if you take a matrix A and a matrix B and you multiply them, and this one's M by N and this is N by P. B times A is going to be N by P and P by M. Sorry, no, not even that. N by P and M by N, and these are not the same. This does not work where this does work, so that's one quick example to knowing why it's not commutative. But let's say you had what we call a square matrix, where the rows and columns are equivalent. 2 by 2 is an example. So go ahead and do this quick counterexample, just to get some practice in. But take a second to do negative 2, 3, 7, 1. And 5, negative 1, 4. Go ahead and figure out what these are just for the practice and see if they're the same. So I'll give you guys a second to do that. Go ahead and pause it. Right here are your answers. These are most definitely not the same. Not equal. Not equal at all. So multiplication, matrix multiplication is not commutative. So not commutative. But here is another interesting question. Consider all matrices that are 2 by 2, right? And the operation multiplication. Is it a group? That is my question to you. See if this has the structural integrity of a group. All right. Operation number 1, closure. All right. If I have two 2 by 2 matrices, do I get a 2 by 2 matrix? Let me rewind and write it like this. Do I get a 2 by 2 matrix? Yes, I do. So we are closed. 2 by 2 matrices with multiplication, we're closed. If I multiply them, all right, don't forget, like, you get rid of the 2. So if one matrix is 2 by 2 and the other one is 2 by 2, the final matrix is going to be the outermost dimensions. So the rows from the first matrix and the columns from the second matrix. So this will still be 2 by 2. It used to be R closed. Do we have associativity? Do we have associativity? Yes, we do, because matrix multiplication is associative. I'm just going to move on from that one. Do we have an identity element? Ooh, now we're getting more interesting. Do we have an identity element? Right. Is there a matrix such that if A times I is equal to A, do we have this thing for 2 by 2 matrices? Think about that for a second. Or if we can discover it, then it exists. So here we go. Let's just figure out what it is, if it does exist at all. Right, let's give ourselves a matrix A. Let's call it A, B, C, D. And let's call I E, F, G, H. And let's call it X, Y, Z, W. All right, so we need it to be the case that we need to figure out what x, y, z, and w are such that A, B, C, D times x, y, z, w is A, B, C, D. So this is going to turn into a little system of equations. Here we go. So A, B, X, Z. So we have A times X, B times Z. A times X plus B times Z. That should be A. AY plus BW should be B. CX plus DZ should be C, and CY plus DW should be D. All right, so we have a system of equations here. Notice that I have two equations with very similar variables, so let's go ahead and solve that system. Right. All right, so I have A x plus b z equals A, and I have cx plus dz equals C. And then I want to eliminate these things, so I'm going to focus on eliminating x. So I'm going to multiply this entire equation by C. I'm going to multiply this entire equation by A, and I get CAX plus CBZ is equal to AC. I get CAX plus DAZ is equal to AC. And if I go ahead and I subtract these two equations here, I get a 0. I get a, let me go ahead and make it alphabetical, BC minus ADZ equals 0. All right, cool. Similarly, I can do the same thing with the other one. So AY plus BW equals B. CY plus DW is equal to D. And then if I do the similar process, I'm going to multiply this thing by C. I'm going to multiply this thing by A. And I get, what do I get? I get CAY plus BCW equals BC. I get CAY plus DAW is equal to DA. And then if I subtract these two things, I get BC minus AD times W is equal to BC minus AD. All right, this one is super easy to solve. Let me go ahead and do this actually. 1 second. All right, so we're over here. I'm getting better at this mid-video. We have these two equations, but the second one down here at the bottom is much nicer because BC minus AD and BC minus AD disappeared. W is equal to 1. When we know now that W is equal to 1, put it back into the original equation. So W equals 1. That implies that Y is equal to 0. Back up here, we have Z must be 0 in order for this equation to be true, which implies that X must be 1. And there we have it. That we have solved this bizarre system of equations. 1x y, z, w. So an underwhelming answer to a complicated question. The identity matrix is 1, 0, 0, 1. And if you don't believe me, just go ahead and check. So if we have a matrix A, B, if we have a matrix A, B, C, D, and we multiply it by 1, 0, 0, 1, we get A times 1 plus B times 0, that's A. A times 0 plus B times 1, that's B. C times 1 plus D times 0, that's C. And C times 0 plus D times 1, that's D. Look at that. We have an identity matrix for 2 by 2 matrices. Cool. All right, let's keep going. All right, this is the last thing I want to do. I want to look at matrix multiplication one last time in terms of does a 2 by 2 matrix have an inverse? Does it definitively have an inverse? Does it sometimes have an inverse? Does it never have an inverse? So we are going to look at inverse matrices for 2 by 2. Right, we could generalize this to larger things, but it requires an intense amount of will and algebra. All right, so we need a matrix, right? Inverse. We need a matrix. Does every matrix, A, B, C, D, have another matrix, X, Y, Z, W, that equals the identity matrix 1, 0, 0, 1? Right, that is the question that we care about here. So let's do the same thing. Let's get a system of equations and just power through it. So AX plus BZ is equal to 1. A times X, B times Z is equal to 1. CX, C times X plus D times Z, that should be 0. We have AY plus BW is equal to 0, and CY plus DW equals 1. Here is our system. Let's solve it. Actually, wait, before we solve it, go ahead and try yourself to solve this system of equations. We are looking for X, Y, Z, and W that satisfy these equations. A, B, C, and D are all scalar quantities. So let me go ahead and I'm going to proceed, but I'm not asking you yet to follow me. Go ahead and pause, but I'm going to go ahead and copy this, paste it there, drag it up. All right, so we have this system right here. We're going to do something similar. We are going to multiply this thing by C. Let's multiply this thing by A. And then we get CAX plus BCZ is equal to C. We get CAX, we can get rid of this, plus DAZ is equal to 0. I'm going to go ahead and subtract these two things. That goes away. We have BC minus AD all times Z is equal to C. And we have Z. Boom. C divided by BC minus AD. Cool. Let's proceed. Let me go ahead and copy this. Put it over here. Let's do the same thing, but let's get rid of Z. All right, let's get rid of Z. So I'm going to go ahead and multiply the top equation not by C. So actually, yeah, don't want this C. Give me 1 second, guys. I'm going to go ahead and pause and then come back. All right, so we want to multiply this thing by D and multiply this thing by B. So we get A dx plus B dz is equal to D. We get BCX plus B dz is equal to 0. We subtract these two things and we get AD minus BC x is equal to D. So x is equal to D minus AD minus BC. Cool. Oh, what happened here? I'll look into that later. All right. So let's go ahead and look at this system of equations. So we're going to be dealing with this thing twice. I'm going to go ahead and put it over here. All right, so similar situation. Let's just go ahead and solve it. You guys can probably beat me there, especially since I have to deal with this writing pad. All right, so I'm going to multiply this thing by C. I'm going to multiply this one by A. C-A-Y, C-A-Y plus B-C-W, A-D-W is equal to 0 and A. This one over here is going to be, just finish this one actually. I'm going to go ahead and subtract these two equations. I'm going to get 0, I get BC minus AD. W is equal to negative A, and W is equal to A divided by AD minus BC. Over here, I'm going to multiply this thing by D and B, and I get A DAY day plus BDW is equal to 0. I get BCY plus BDW is equal to B. I'm going to go ahead and subtract these two things, and I get 0. I get, I did something wrong here. No, I didn't. DAY BC, so that's AD minus BC Y. This is 0. This is negative B. And then over here, I get Y is equal to negative B, all divided by AD minus BC. Cool. All right, so in doing all of this miserable algebra, we got that X, the inverse matrix is, let me find it, it's right here, D divided by AD minus BC. Y is right here, negative B AD minus BC. Z is right here. It's still messed up. It was, what the heck happened? I don't know. Oh, I know what happened. Well, Z is, let me just go ahead and write it. Z, you guys should have it on your page. Z is C, negative C actually, AD minus BC. And then W is A over AD minus BC. So our inverse matrix. All right. If I have a matrix A, B, C, D, and I want to get 1, 0, 0, 1, I have to plug in. Oops, sorry. D AD minus BC. This is going to be negative B AD minus BC. This is negative C AD minus BC. And this is A AD minus BC. And that is our inverse matrix. And that's a lot. One easier way to write it would be just to factor out the AD minus BC in every term. And that would be D A negative B negative C. And that is the way we normally write it, right there. That is our inverse matrix. All right, so here's a question. Is there a inverse matrix for all 2x2 matrices? So in other words, is there an inverse for every single possible 2x2 matrix? And the answer is no, because if AB minus BC is 0, then this is undefined and we don't have a matrix. So the group of matrices 2x2 and multiplication does not have an inverse for every single element. So this is not a group. Nope, not a group. Right. We call matrices that are not invertible, we call them singular, but you could also just say not invertible. And the thing that determines, as I've just said, the thing that determines whether a matrix is invertible or not is this number right here. Throwback, what do we call this expression? We call it the determinant. AD minus BC. We've seen this before, right? So one notation that we use is this. This might be familiar to you. AD minus BC. We call this the determinant of this AD minus BC. And so the inverse of a matrix A, just to put it all into one page, given a matrix A, B, C, D, the inverse of this matrix is 1 over AD minus BC, the determinant, right? The notation we normally use is A, B, C, D with these bars. We do not have these little indentations here. Times, this is a number, times A and D switch, and B and C are negated. Right. So that was a mouthful, sorry for the incoherency there. Right. So, matrix multiplication, not a group. It does not have an inverse. Right. The question I leave you with is, consider the group of all invertible 2x2 matrices. And the operation multiplication. Is this a group? I will leave that for you to determine. The hardest part about this is showing that the product of two invertible matrices is also invertible. But once again, I'll leave that for you to figure out. All right, so before I let you go, I want to just recap what we did. We talked about matrices. We talked about how we defined them before as just a box of numbers, but now we're starting to give them operations, and we're going to use those operations to do further algebra. We talked about what multiplication is in terms of matrices. It's not obvious, but we talked about it in the context of a word problem, and then we did it in general with regular old matrices. Then we started looking at whether or not matrices were groups and things like that. So we did a lot here. We also talked about the nature of multiplication. We talked about what the identity matrix is. It's 1, 0, 0, 1 for 2 by 2. We can generalize that more later. And we also talked about what the inverse of a matrix is. And it required a lot of algebra, but the final answer was pretty straightforward. So I hope most of that made sense. This is my first functions video. It was kind of challenging, but hey, we're here at the end, and we are hanging in there. Hope you guys are doing all right. Let me know if you need anything. I am always just an email, a remind message, or yeah, if you need me, let me know. Have a good one, guys.